Hello. In the previous video, I explained the t-statistic approach, and I forgot one page. But it's simple. You remember, depending on the significance level alpha, the z-value changes. Z alpha over 2 is given by these numbers when you have each of these significance levels. So they can be found directly from the normal distribution table. And in the homework, you have to learn have to do it by yourself. I give you a little bit non-standard significance level and ask you to calculate this and use Excel. And also these numbers I don't recommend, but it's not bad if you memorize these numbers. They are so commonly used, and we already used them as confidence intervals. In the confidence intervals, we needed these numbers, so it's not bad to get more familiar with these numbers. Or you can use these numbers in the homework. So I'll make it a cheat sheet. Okay, the third method is the critical value approach, and the critical like so. Now there is a trend. P-value. So to calculate the p-value, you have to first calculate the sample mean, and then t-statistic, and then p-value. And then we learned t-statistic. To calculate t-statistic, we only have two steps. Calculate the sample mean, and then standardize. Right? Now we don't do the standardization. So critical value approach directly goes at the sample mean. The decision rule is like this. You are going to reject the null hypothesis if the sample mean itself is too much different from the belief. Don't reject if close enough to the belief. Then, as usual, then how different is too different and how close is close enough? This is mathematical definition of close enough. So the threshold, I mean the mu0 minus m and mu0 plus m are called the critical values, right? Lower critical value, upper critical value. So I would better say endpoints. Two endpoints are the critical values, and we usually denote them as critical value upper critical value as C subscript U, which equals to mu0 plus m, and CL lower critical value as mu0 minus m. So and we say the interval between the critical values is called the acceptance region, because if x bar falls between them, then h0 is not rejected, and often it is said h0 is accepted. On the other hand, if the area outside the critical values is called the rejection region. Literally, if x bar is outside, if x bar is on the rejection region, h0 is rejected. So that's where we reject the null hypothesis. And by the way, this form looks familiar because this is what we learned in the confidence interval chapter. And yes, it's very closely related to the confidence interval, and we are going to compare this with the confidence interval later. So wait a few minutes to get there. So in the picture graphically, this is what you're doing. So suppose that I believe that students spend 30 hours on average for midterm exams. And then, so my belief was 30 hours, but suppose that it's acceptable to have between 29 and 31. So you cannot, even if 30 hours is true, but your sample mean cannot be exactly 30 hours. There will be a little bit of error, and I'm going to tolerate up to 1 hour. I'm going to accept 1 hour error. As much as 1 hour is acceptable, but any error greater than that will reject the null hypothesis. I'm going to give up my belief if the data is larger than 31 hours or smaller than 29 hours, right? So rejection region will be outside this dashed points. Okay, that's the idea. And then how do we choose the decision rule? How do we choose the critical values? It is coming from the t-statistic. As I said, we reduce there, so p-value require 3 steps to calculate the p-value, and we reduce 1 step to calculate the t-statistic. Instead, we reduced 1 step to calculate the t-statistic, but instead this step goes to the significance level. We have to transform significance level into a z-value. So 1 step, reducing 1 step in calculating the statistic, we add another step. We have additional step in the comparison counterpart. And same thing here. Critical value does not require any special step, like except for calculating the sample mean. So it ends at 1 step. But on the other side requires additional step. So significance level is given, and then z value should be found, and then we need another step. That's what we are doing here. So compare. First, let's think about the t-statistic decision rule. So I will use the acceptance rule. H null is not rejected if the standardized difference t is small enough, close to zero enough, close enough to zero, at most z alpha over 2, and it is assuming the significance level of alpha. So then I am going to replace t with its underlying formula. So this inequality can be written as, so this is the condition to accept H0, to not reject H0, and then it can be written as this. So t statistic must be between plus minus z, and t itself can be replaced by this. And what we need here is we need x bar. We are going to isolate x bar in the middle and move all the other terms to the outside terms. So isolate x bar here and multiply s over square root n on both sides and add mu 0 on both sides. Then you will get this inequality. Remember, this is equivalent to this. So this was the condition to not reject H0. So that means based on the t-statistic, this was the condition to not reject H0. Then based on x bar, you have to use this as the condition to not reject H0, right? And yes, so that shows that this is the lower critical value. This is the upper critical value. Exactly what we wanted. So if x bar lies in between two critical values, H0 is not rejected. But if it goes outside, then you reject the null hypothesis. So critical values are given by this, right? And as I said, it's very much similar to the confidence interval. Of course, details are a little bit different, like mu0, confidence interval uses x bar here, but we have to use mu0 because we are assuming the null hypothesis is true at this time. And later I'm going to compare it even more. So wait for that a little more. Then finally, the decision rule based on the critical value at the significance level alpha is given by this. Reject H null if x bar is too small or too large. And don't reject if x bar lies between two critical values. So intuitively speaking, the x bar, your observation, your sample mean must be within plus minus zs over square root n around mu0. So this plays a role of the margin of error. So you allow this much error around your belief. If not, H0 is rejected. So your belief is here, but you allow certain margin of error, and if your observation is even outside of that, then your belief is rejected. It's wrong. And now let's compare the confidence level and critical values. Confidence level took this form, and critical values took this form. Structure is parallel. So the major difference is, first, confidence level was for estimation, and it was centered around the point estimator, the sample mean. The sample mean was the point estimator, and we wanted to estimate the population mean. But in critical values, so the situation is a little bit different. If in the critical values, we have our belief about the population mean, but we are yet to calculate the sample mean. So we are going to calculate the critical values first from our belief, and then we will compare the sample mean with this guy. So this interval is made for the sample mean. Sample mean will be compared with this interval. So it's centered around your belief. So it is coming from the belief and compared toward the sample mean, but in this case, this is the other way. You start from the data sample mean, and you want to compare this with the true parameter. So later we calculate the probability of containing true parameter. So it's different. That's the major difference. And confidence interval, as I said, so it's correct if it contains the true parameter. So the purpose, the goal of this interval is to contain the true parameter. But in this case, critical values, it is not a goal to contain the sample mean, but the purpose of calculating this interval is to be compared with the sample mean and make the decision based on the comparison, right? And finally, another annoying thing here is confidence interval has same alpha. The role of alpha is exactly the same. Z alpha over 2, Z alpha over 2. They are the same alpha, but their names are different. Here, confidence level alpha was the error probability. And people don't usually say error probability is 1%. More often, people use the confidence level, which is 1 minus the error probability. So confidence level, confidence interval is based on like 90% confidence level or 95 or 99%. So it's using 99, 95, 90. But critical values in the hypothesis testing, we directly use alpha, 1%, 5%, 10%. That's I also don't like it. I hate the convention. I don't know why it happened, but I guess historically, at the beginning of these methods, different statisticians developed the framework independently, but later on they are in the end they found to be similar. So we unify all the frameworks into one. But many years ago, they must be totally different areas, right? Some statisticians only study estimation. Some statisticians only consider hypothesis testing, but in the end, it happened to be the same structure, so the naming is not consistent to each other. Okay, and finally, another difference is that p-value, and let me compare critical value with p-value and t-statistics. P-value and t-statistic do not depend on significance level alpha. So that was one advantage of using them, because you may choose significance level if you want. Significance level itself is ad hoc. So you may choose them whenever you want. So these are particularly useful for programs. When you write a program to calculate the result, then simply you can calculate the p-value and you just do the last step. Compare that with alpha by choosing your own alpha. That's typical structure of a programming. But critical value is used in a different way. It depends on the significance level but does not depend on X bar. So then it is more convenient when you have to repeat the same hypothesis testing to different sample. For example, suppose that I'm regulating some drugs, medical drugs, and the medical drugs have to contain the correct amount. And then what I'm going to do is I'm going to use 1% critical significance level, and I have to test many different brands. So then what I can do here is I make one critical value and apply the same critical value for this drug and to another drug and another. So then actually it is easy. If you use the p-value method here, then from each drug you have to recalculate p-value. So it requires more computation. But when you have a critical value, so simply you set a threshold for every sample mean and just calculate sample mean and make the decision. Could be more convenient, easier. So that's the usage is quite different. And we are going to see how we use the critical value in the next chapter next week. So then the idea is it does not depend on the sample mean. So if you have to apply the same hypothesis testing to different sample means, critical value is more useful. That's the idea, right? And finally, I think I already said finally in the last page, but another finally. If the significance level increases, the idea is you reject more. So that means you reject more, so the rejection region should extend. So that means acceptance region shrinks. So the critical values should be closer to the belief. Oh, it's going the other way. Excuse me. It's totally wrong. Critical value should move toward the belief, mu0. And there is another change you can think of, like if the standard error increases, it makes the critical values wider because you have to allow larger margin of error. So also the intuition behind these two is the same as the intuitions behind confidence intervals we discussed in that chapter. So particularly important is the significance level. When you increase alpha, you reject more, so your acceptance region shrinks. That's the idea. So critical value has to be closer to mu0. The margin of error should be smaller. Okay. Okay. In the next video, I'm going to show you two numerical examples. So thank you for watching this, and see you in the next video.